Hi guys, good morning. It's another lovely Tuesday. I hope we're all having a great day. Today we're going to be doing physics. Okay, so we're going to do physics today. Now, before that, I just want to tell us some fun facts. Before we go into our topic, the topic we're going to be teaching for today, I want to tell us some fun facts in physics. Okay, just one fact anyway. That's all we have time for. So let's look at this. Let's look at this person. Now, I think we know Albert, all of us know Albert Einstein, or we've heard about Albert Einstein. Okay? So, of course, Albert Einstein has contributed so many things. He has contributed to so many things in physics and life and in what we, in the life we live today, right? Okay, but I just want to tell you one of that's one of his works that is so important to us. Okay, well, not the most important, but just one out of all the things he has done. So let's look at this. Look at. Okay, now, first of all, let's talk about Albert Einstein's contribution to daily life, right? Okay. Now, have you heard of a GPS navigator? Okay, some of us we heard about Google Maps. At least we've heard about it, even though we don't drive. Our parents probably drive, and then they might use Google Maps, or we've heard about Google Maps. Okay, so you know what it's used for. You use it to find your way. Sometimes maybe you're going to a place that you've not been to before, and you just have the address, the location, and that kind of thing. You just use the Google Map to locate that place, right? Okay. Now let me tell you how Albert Einstein actually helped us with GPS navigators. Okay. So look at this. I'll break it down step by step, and then you'll see why Albert Einstein helped us with this. Okay? So look at this. Now, first of all, the first fact I'll tell you is that Einstein published the theory of relativity. It's a very big field on its own anyway. But he published a theory of relativity in 1915. Okay, that's fact one. Now, fact two, the theory explains so many things, and one of the things that the theory explains is why the clocks on Earth here are behind those on satellites. Like the ones on satellites are faster by about 38,000 nanoseconds. Okay, so that's one of the things that Albert Einstein's theory of relativity explains. Okay, now third fact, just follow me. Third fact: GPS navigators that we use, these Google Maps that you have on your phone, that will tell you, okay, there's hold up here, this line is red, this other line is yellow, then you know where to pass. Good. Now, these GPS navigators, they work by measuring the distance between a point on the Earth and these satellites, okay? And these satellites that are orbiting around our Earth, okay? Now, let me now put it to you that if Einstein did not postulate the theory and then prove the theory of relativity, okay, and then publish it, you would probably say, okay, I'm going to Lagos. You've not heard of Lagos before. I want to go to Lagos, and then you end up in Abuja because your GPS navigators just won't work. So the mind behind one of the major it's not the only thing. One of the major reasons why we can use GPS navigators today is because of this theory of relativity. So that's what helps us to manage the relative difference between the orbiting satellites and Earth here. So think about it. Without Albert Einstein, you probably start from Lagos and find yourself in Abuja, or you say you are going to Akure, and before you know it, you are in Kaduna. So you can see we should be thanking Einstein for giving us this theory. That's just one of the things that he actually contributed. So So I'll tell you more in the next class, okay? Tell you more, maybe about him or about somebody else. So let's move to what we have to do today. Okay. So now, the things you're supposed to know today, if you actually watch this video and you follow me step by step, what you would actually know, you'll be able to find number one, distance, number two, speed, you'll be able to find velocity, and you'll be able to find acceleration. Now, if you're a physics student, you're familiar with these terms. You've heard about distance. Even though you're not a physics student, anyway, you've heard about distance. You've heard about speed, okay? So I'm going to now tell you, some technical things about these quantities, okay? So the title of our class, or the topic of our class today is speed, velocity, and acceleration. Speed, velocity, and acceleration. Okay, so now look at this car. Look at this car. Put your eye on the car. It's about to do something. Okay, so it has gone. It has gone away. Okay, now that car covered a particular distance. It's moved from, you saw it on the screen, it moved from this point to that point, right? And you can't see it again, so it has gone. Now, that car covered a particular distance and it's moved at a particular speed. The rate at which it's left the screen is what we now call this speed, this quantity called speed. We all know that distance has to do with position and the portion covered. Okay, now speed, what is speed? Okay, now, so we can say that, are you ready to see this? Speed is the rate of change of distance. Okay, the rate of change of distance, or you can say the measure of how distance changes with time. So in speed, you are two-dimensional. You're looking at distance and you're comparing it to time. You're like, okay, how far is this person moving? How far is this car moving at this particular time or within this particular time? Okay, so it's a measure of how distance changes with time. It's not an abstract thing. It's not an abstract thing. All of you have seen cars on the road, right? Okay, they're covering a distance, or buses, they're covering a distance, right? And they're going to use a particular time to cover that distance. Okay, yeah. So, for example, you're going from, let me use somewhere that, I don't know if everybody is familiar with Lagos anyway, but let's assume you're going from Ikeja to, let's say, Oshodi or something like that. Okay, now, the bus is moving from one point to another point, and there is a fixed distance that you cover, right? Now, speed is a measure of how does this bus cover that distance within this particular time. Okay, so follow me. Now, let's be mathematical now. Okay, how do we represent this? So speed, in essence, is just distance over time. Distance over time. And we can say d over t. Okay, now take notes that speed is a scalar quantity. When I say the word scalar, I want you to know that scalar means it has magnitude, that it has a value, but it doesn't have a fixed or a specified direction. Okay, I'll tell you why that is necessary as we know. So speed equals to distance over time, which is d over t. Put it here, put it here, put it here, put it here. If I ask you, let me be able to get it back from you. If somebody asks you around you where you are, you should be able to say it, okay? So the SI unit, I don't know if some of us are familiar with the SI unit system. It's the standard units, the standard units that we use in physics. So the SI unit of speed is meters per second, or you can say meter second raised to the power -1. It's the same thing as meters per second. So that's on speed, okay? We're still going to come back to this anyway. Now, average speed. When do we have to deal with average speed, okay? Now, when the rate of change of distance is not uniform, we can find the average speed. For example, the car is not moving at the same rate. You understand? Okay, you are going to from Guagalada to, which other places in Abuja? From Guagalada to maybe I don't even know. FCT is the capital. Okay, so you're going somewhere now. Although there's usually not much hold up in Abuja compared to Lagos. So let's come back to Lagos. Let me look for a hot point. Now you're going from Lagos Island to Lekki, for example, Victoria Island to Lekki or something like that. Now you would notice that at some point you stop because there's a little traffic in front of you. The road is full of traffic, so you stop at a point, you move, you stop, you move, you stop, and all that. Now, the speed that you're using to move and stop, move, and stop cannot be uniform, okay? It's not going to be uniform because it's not going to be the same speed throughout. So in this case, you can find the average speed of the whole journey, okay? So you would say the average speed is the total distance covered over the total time taken. So it gives you an average of how that car or how that vehicle moved from one place to another, okay? So that's average speed. Now for velocity, pay attention, for velocity. Now, velocity is the rate of change of displacement with time. So now it is the same thing as speed, but it's in a specified direction. You see what I was telling you then about speed being a scalar quantity? Yeah, velocity is not a scalar quantity. It's a vector quantity, and it has both magnitude and direction. Okay, so it's the same thing as speed, but instead it's in a specified direction. Okay, now, so velocity, like I said, is displacement over time. Okay, now look at this car. You can see that. Now, if you want to talk about the speed at which this car is moving, we can just say, okay, the speed of the car is 20 meters per second. But if I say the speed of the car is 20 meters per second to the right, I have told you where the car is moving to, the direction the car is moving to. You can see the arrow there. So that is the major difference between speed and velocity. Okay? Now, the SI unit of velocity is also meters per second. It's the same unit, SI unit with speed. Okay, so follow me. Now, let's look at this. We have something we call a displacement time graph. Okay, now what is this all about? What's this all about? Okay, when we plot the displacement of the body against time, okay, that's when we obtain a displacement time graph. For example, we say, okay, this person went so displacement, went from 0 meters to 20 meters in 5 seconds. Okay, after that, from another 10 meters in another 10 seconds. Okay, so when we plot that in a graph, okay, it becomes a displacement time graph. Okay, so look at this is an example of a displacement time graph. Although I didn't use any values here, this is an example of a displacement time graph. Now, there's something we call the slope of the graph. Okay, now the slope of a displacement time graph, delta, is usually delta D. That's change in displacement over change in time. When you see that sign that looks like a triangle, that delta sign, it means change in. So change in distance over change in time. Now the slope of displacement time graph is velocity. Because we've already said before that displacement over time is velocity. Okay, so remember that when you're talking about the displacement time graph, the slope is velocity. Okay, now also, let's now look at acceleration. Acceleration, what's the big thing about acceleration? Acceleration is a step further than speed. Now, acceleration talks about comparing the speed at which the speed with which the vehicle moves to the time it takes to move that distance, or the distance it's moving. So, for example, have you ever been in a bus before, and then suddenly the road was very busy, and there were lots of vehicles on the road, and then all of a sudden everybody started moving, and then all of a sudden you feel this lurch, as if you're being propelled forward. You know, that's where the driver accelerates and the car moves with like a lurch and moves forward quickly. That's what we call acceleration. Okay, that's acceleration. That's a pure example of acceleration. Now, in physics, we say acceleration is the rate of change of velocity, or how velocity changes with time. Okay, is the rate of change of velocity or how velocity changes with time. Okay, now there's a second phase to this acceleration. It's two-phased. There's what we call the positive acceleration, and there's what we call the negative acceleration. Now, positive acceleration involves starting from a small speed and then moving, launching forward or propelling yourself, you know, with a faster speed. Now, but the other negative acceleration, which we also call retardation, usually involves a decrease in your speed. Now, let me give you an example. You're going in a car or a bus, and then you notice that, okay, you were moving freely before, and all of a sudden there's a lot of traffic. You can see vehicles ahead of you. What do? Do you just keep going, maintain the same speed, and just keep driving? If you do that, you'll probably end up with an accident, which is not something we all want to be involved in. But when you notice those vehicles piling up, the next thing you think of is to reduce the speed, right? And then you retard. You stop that acceleration if you were accelerating before, and then you start the retardation motion. Okay, so you retard. That's what we call the negative acceleration. Okay. Anyway, let's continue with this. So acceleration in physics, we'd say mathematically, it's the change in velocity all over time. Now, change in velocity. So we can now interpret that with letters. So we have A equals B minus U over T. Now, of course, you need to know that change in velocity means the final velocity minus the initial velocity. So B is the final velocity and U is the initial velocity. Okay? And then T is the time. All right. So the SI unit of acceleration, the unit with which we measure it, is meter per second square. I told you it's one step ahead of velocity. Velocity is meter per second. So acceleration is meter per second square. Okay, or you can say meter second minus 2. Okay, so that is acceleration. That's acceleration for you. Now, there's also another type of graph, which we call the velocity time graph. The velocity time graph. Now, I think you should have a hint already what this means, since I've told you what displacement time graph means. Okay, now a velocity time graph is a graph that has velocity plotted against time. So when we plot the velocity of a body on the y-axis and time on the x-axis, we obtain what we call a velocity time graph. So it is the study of, okay, how comparing the velocity of a body with the time. Now, this is an example of a velocity time graph, okay? So in this case, we are looking at, if we're going to get the slope of the graph, we are going to have to do change in velocity, that's delta V, change in velocity, all over the change in time. That's delta V all over delta T. Okay, so delta V over delta T. Now, the slope of the velocity time graph now is acceleration. Every single quantity here is intertwined. You know, speed, velocity, acceleration, distance, they are all, I don't know, they are related to one another. So the slope under, if you of a graph that has velocity against time is acceleration. Remember that acceleration is velocity over time. Now, another funny thing, when you plot a velocity time graph, okay, the area underneath that graph is also the distance covered. It's funny and it's a beautiful, you know, thing. So the area under the graph gives the distance covered. Okay, I will tell you how to plot a velocity time graph before the class is over. Okay. Now let's take some examples on, you know, everything we've said. Let's see how if we can calculate one or two things or do some little calculations. Okay. So look at question number 1. A motorcycle starting from rest moves with a uniform acceleration until it attains a speed of 108 kilometers per hour after 15 seconds. So we are to find the acceleration of this motorcycle. So motorcycle starts from rest and moves with a uniform acceleration, meaning the acceleration is uniform across that motion. And it attains a speed of 108 kilometers per hour after 15 seconds. We have to find the acceleration, okay? So let's try to solve it. Let's try to solve it. So this is the question again. Let's solve. Now, before we can solve, we need to list out parameters. I always say this, that you should know what you have so that you can find what you do not have, right? So we need to know what we have. Now, first of all, if the body starts from rest, okay, rest, meaning that, okay, have I said this? If a body starts from rest, it means its initial velocity is 0. Do you understand? Now, if a body starts from rest, it means it wasn't moving at that time. Before it started moving, it wasn't moving. So the initial velocity of that body is 0. So once you hear the word, okay, a body starts from rest, oh, that's a 0. That's a 0. The initial velocity is 0, okay? So U equals to 0 meters per second. Now, the next thing we need to write out that we have is it attains a speed of 108. That's the final velocity. Okay, that's the final velocity. Now, but you can see that there's a slight problem. Unit is in kilometers per hour. So we have to change that to meters per second. You cannot work with two different sets of units. Remember, our time is in seconds, so you cannot work with two different sets of units. So you need to change from kilometers per hour to meters per second. And how do we do that? Of course, we know that 1,000 meters make 1 kilometer, so we multiply by 1,000. And we know that there are 3,600 seconds in an hour, so we divide by 3,600. And then we get 30 meters per second. That's our final velocity. Okay, one more parameter. Our time. That body took 15 seconds to complete that short motion, right? So our time is 15 seconds. Now, what were we asked to find? You have to take it step by step. There's nothing difficult in this. What you need to do is analyze it. Take it step by step. Okay, get what you've been given and figure out, okay, what am I supposed to find and how do I find it? So here we are to find the acceleration. How do we find it? We talked about the formula for acceleration before, so I'm going to remind you. Now, remember that acceleration A is V minus U over T. Put it here, put it here, put it here, put it here. V minus U over T. So let's substitute our values. We have 30 minus 0 over 15. It's as simple as that. It's as simple as that. Just take it easy and try to take it one step at a time. So 30 minus 0 is 30. So 30 divided by 15 is 2 meters per second square. Another thing is your units. Units, very important. I cannot afford to write meters per second here because that's the unit for velocity. So you must be very careful with SI units in physics, okay? So remember that the unit for, and another day, another time, I will also show you how to derive all these units. They are very easy and they are not complicated, okay? Now, let's look at one more example before we, close for the day. So look at this. A train starts from rest, okay? A train starts from rest. What's rest? We become acceleration after rest. But what is rest? Okay, let me just tell you. Of course, you can't really tell me. But, rest, a body starts from rest simply means that the velocity, the initial velocity of that body is 0 meters per second. Don't forget that. Okay, so train starts from rest and it moves uniformly at the rate of 2 meters per second square until it attains a maximum velocity in 20 seconds. Okay, so now it maintains this velocity for 60 seconds and then it retards. I told you the meaning of retard. It retards uniformly to rest. It retards back to rest after 20 seconds. Now, number one, we're to draw the graph of the motion. Okay, draw the graph, that's the velocity time graph of the motion, and find the maximum velocity. I want to find the maximum velocity. Okay, so let's look at this. How do we draw the graph? Let's start with that. Okay, so we have to draw the graph first of all. Now, before you do anything, you should remember that your two axes are your velocity axis and your time axis. Okay, so you put that first. You put that first. Now, remember that you're to start from rest, which means 0 meters per second. So 0, put your 0. Now, the body accelerates. You're going to use an arrow to show acceleration. I'll show you now. So this is how the acceleration looks like. Okay, it's moving with an increasing speed. So it's accelerating. Okay, so it's going up. Good. Now, you need to also label, let's just use A as our point there. Let's just put A as our point there. Now remember that it attains maximum velocity at that point A. So I'm going to put a V there to indicate the maximum velocity. Okay. Now this whole thing is what we refer to as the acceleration part of the motion. This is the acceleration part of the motion. Okay. Now the next thing. It attains a maximum velocity of in 20 seconds. In 20 seconds. So you need to also put 20 seconds on the time axis. Okay. So on the time axis now, we are going to put 20 seconds there. You can just, I'm just using letters, so you can use E or whatever letter you want, but you should be consistent with your lettering. So this is 20 seconds now. It has attained maximum velocity V. Okay, let's move on. Now, it maintains this velocity. It does not accelerate. It does not speed up. It does not speed up. It doesn't change the speed. It maintains that speed. Okay. So I'm going to show you an arrow to draw for you to show that it maintains the speed. Okay. So look at this. A straight line. A straight line shows that it maintains. Let's call that point B. It maintains that speed for 60 seconds. So this is what we call the constant velocity. It maintains that velocity. Okay. It keeps going with that same velocity. Now, for 60 seconds, now you won't put 60 on the time axis because remember the body has already moved for 20 seconds previously. Okay, so now you're moving for an additional 60 seconds. So remember, it's like a cumulative, you know, cumulative process. So you're going to add another 60 seconds to the 20 seconds that have moved previously. So that's going to give us 80 seconds. Okay, that's going to give us 80 seconds. So that's 80 seconds. Now, after this, we've done the acceleration part of the graph. We've drawn the constant velocity or the uniform velocity part of the graph. Now, the body retards. Probably some vehicles in front of it began to pile up and they were stopping because of maybe an obstruction in front or something, anything. So the body has to now come to a stop. The body has to come to a stop. The train retards. So the person driving or the person manning the train retards uniformly to rest back to a stop. So retards uniformly to rest in 20 seconds, after another 20 seconds. So look at that's the arrow for your retardation. Okay, that's the arrow for your retardation. We can call that point C. And remember that this is the retardation part of the motion. Now, remember, it took 20 seconds for that body to stop, for that body to come to a stop. It took 20 seconds, right? Okay, are we going to try 20? No. Remember that the body has already moved for 80 seconds previously. So an additional 20 seconds would just make it 100 seconds. Okay, 100 seconds. So this is what we call a typical velocity time graph. So if you ask you to draw a time graph of the motion, break it down. Break it down. Sometimes there might not be constant velocity. Sometimes if the body just accelerates and retards, you know, but just make sure that you understand the question. If it says it starts from rest and it accelerates, draw an arrow. Constant velocity, maintain that velocity. Retards to rest, you draw an arrow going down. Okay, so this is a typical, you know, example of velocity time graph or the graph of the motion of the body. Okay, good. Now let's look at the next part of the question. So this is our graph. I just carried over to this page. Now the next part of the question says we should find the maximum velocity. Find the maximum velocity. Okay, we've already indicated the maximum velocity previously with the letter V. I hope everyone can see V. You can see V on the graph. Now, but to find the maximum velocity, the maximum velocity will not just jump out on its own. We have to use other quantities to find the maximum velocity. Remember that we were told that the body accelerates at 2 meters per second square, if you remember. The body accelerates at 2 meters per second square, okay? Now, so we're going to use that mixture of acceleration time to find the maximum velocity. So follow me. Now, from the graph, acceleration, now, you know, acceleration normally is velocity over time, right? Now, our velocity for that acceleration part is, we can use that line AE, okay, over OE, okay, over OE. Now, what do we do from here? Remember that the acceleration is 2 meters per second square. And I already told you, even if you don't want to use AE, OE, or those lecturings, but you already remember that the formula for acceleration is V minus U over T. Velocity, final velocity minus initial velocity over T. Okay? That simply means now that we are looking for the final velocity for that first part, just for that first part. That's the maximum. Another one is the maximum velocity now. Okay? So we are looking for V. But we remember that the body started from rest. So it's going to be a 0. From our graph, we can see already that it's a 0 there. And we can also see from our graph that the total time it took that body to accelerate was just 20 seconds. So our time there is also 20 seconds. So V minus 0 over 20 is equal to 2, which is our acceleration. Okay, so we have 2 equals V over 20. And then we can cross multiply. 2 times 20 equals V. And then we can say that our velocity is 40 meters per second. Remember that I said our unit must be the correct SI unit. We shouldn't say meters per second square here because that's for acceleration. So the velocity here is 40 meters per second. Okay, so that's that for maximum velocity. That's for maximum velocity. So I'm going to give you something to do, but let me tell you what I want to give you to do. Then I'll come back and try to help you a little. Okay. So where at home you can just try this out. That's using the same example that we have just treated. I want you to now try to find the total distance covered, and I also want you to try to find the value of the retardation. You know, the retardation part is also in the graph. I want you to try to find the value of the retardation. Now, let me give you some hints. For the distance covered, just find the area. Remember how to find area of plane shapes. Well, I won't tell you, but try to find the area. It's this. Okay, let me just show you this. Let's go back to the graph. Take note that this graph is made up of three different portions: the acceleration portion, the constant velocity portion, and the retardation portion. Now, we have two triangular portions and one rectangular portion. Okay, one rectangular portion. So you can decide to find the area of the two triangles and that of the rectangular portion. Or remember also that this is a trapezium. So you can just go straight ahead, identify the length of the two parallel sides and the heights of the trapezium and get your area. Now, whatever you get as the area is the same thing as the distance covered by this body. Now, the second thing I asked you is to find the retardation. You can see the part for retardation there. Now, remember the formula for acceleration, v minus u over t, right? Okay, let me just help you out a little. Now, the body is retarding. It's retarding. It's going to rest. So the final velocity will be 0. The final velocity will be 0. Now, I won't tell you what the initial, but let me give you a hint. It started from point B, right? The retardation starts from point B. So you can figure out the velocity in point B. That's the initial velocity. And I've told you the velocity at point C is 0. Now, the time taken to cover that retardation motion is between D and C. That's 100 minus 80, which is 20, right? So you should be able to get the retardation. All right. So now, if you do it properly, if you do it well, if you do it accurately, you should get these answers. Your answer for the distance covered should be 3,200, and the answer for the retardation should be 2 meters per second squared. Now, you notice that I did not put a minus in the retardation. Now, why did I not put a minus in the retardation? When you say retardation, you have already put in that negative into the word. For example, when I say negative acceleration, it means the same thing with retardation, right? Now, if I say the negative acceleration is minus, I'm contradicting myself. It's like a repetition, which is unnecessary. Now, if I tell you to find the acceleration and the body was actually retarding, then you would put a minus sign, right? But since I just said find the retardation, you already know that I'm asking you for the negative acceleration. So you can just go straight up and do that. So I'll be looking forward to your feedback on your answers if you got it right. If you didn't get it right, if you have some questions on this that you don't really understand, or if you just have something to say about speed, velocity, and acceleration, I'll be looking at your feedback in the comment section. Now remember to subscribe for weekly updates. So next week we would continue from here to pick something else and move further. So it was lovely talking to you guys again this Tuesday. I hope you're going to have a lovely day. Bye.